So the traditional test we do on a starter is a starter draw test where we're going to measure the amount of amperage that the starter uses. So we have some really good rules of thumb. So if it's a 4-cylinder engine, it should not use more than 100 amps. If it's a 6-cylinder, it should not use more than 150 amps. And if it's an 8-cylinder, it should not use more than 200 amps. And that is for gasoline powered vehicles. Diesel powered vehicles will use more current because they have higher compression, more resistance. So those are just the off the top numbers that we normally use. I can research specifications. Sometimes the manufacturer will give me a specification for what their maximum amperage draw is. There's never a minimum amperage draw published. Or they may list the kilowatt rating of the starter, which is very common, just to give us the watt rating of the starter, kilowatt rating of the starter, and not the amps. So at that point, since I know that watts is volts times amps, I can use 12 volts as a rule of thumb to kind of get me a ballpark area and take whatever my kilowatts is divided by 12. And that's going to get me in the ballpark. Keep in mind, as I'm cranking the vehicle over, my battery voltage is going to drop. So I may only have 11 volts. So don't use that as a hard number, but use it as a ballpark. So for example, if I do the math at 12 volts, 1.2 kilowatt starter, that's 100 amps. And I go test the vehicle and I only have an 80 amp draw. Well, remember, there's no minimum. I can always be under. So that would be good. And that's normally where we see those out on a good engine. On the other hand, if I was at 103 or 105 amps, I would need to ask myself, what's the voltage then? Because if the voltage is 11 volts, I need to recalculate what acceptable is for the amps. So I probably wouldn't fail it because it's 5 amps out. On the other hand, if I do the math and on a 1.2 kilowatt starter, 12 volts, 100 amps, and I do the test, I get 150 amps. That's bad. I mean, that is completely out of an acceptable range. So many times when starters go bad, that's what we're seeing is they are completely out of the acceptable range. We're not looking, they're one over, time to replace it. No, that's not how it works. Because even if it's one over and technically it's out of specifications, it's not causing the problem the customer brought the car in for. So if my starter is pulling 105 amps instead of 100 amps, it's not going to cause my battery to go dead. It's not going to cause my car not to start. So therefore, the customer would not have brought the vehicle in for me to find that their starter's drawing 5 amps too much. So in order for the customer to have brought the car in means the car is not starting correctly. So by the time it gets to the point that it's actually a big enough problem for the customer to complain about, want to take the time out of their day, bring the car into the shop and spend money, I'm going to find something substantially out of specifications. And that's why that's why I'm using 12 volts. I'm not worried about 10.5 volts or 11 volts or 12.1 because I'm really looking for something that's completely out of range. And that's why I gave you those numbers. 4-cylinder, 100 amp max normally, 6-cylinder, 150 amp, 8-cylinder, 200. And again, if I'm a couple over, I'm not, it's not catastrophic. But if I'm expecting to see 100 and I get 150, that's a problem. Many times on an 8-cylinder, when a starter goes bad, I'll see 400 amps. I mean, I will see substantially more than the 200 amp max. On the other hand, if I have a starter that's pulling 220, 230 amps on an 8-cylinder, and it takes 5 seconds to start the car every time because of another issue, now the combination of those things could be causing a problem, right? Because the battery's going dead or the battery's not lasting because we're doing a lot of short trips, cranking the car too long. And when I crank it too long, I'm using more of the battery than it's designed to use, plus my starter's pulling more than it should. So we have a cascading effect. So there's not a single thing that's causing the whole problem. So if I fixed the problem with the car, why it's cranking long, the 220 amps probably isn't an issue. If I replace the starter because it's a 220 amps and the new starter is at 160 amps, again, the customer may not have the issue, but there's actually a combination of problems causing the complaint. Only fixing one of them might not get you there. That's why when we do diagnosis, we don't stop necessarily at the first thing we find wrong. Oh, it's going dead because it cranks too long. Well, we still want to look at other things. And especially if the customer's complaining of a battery going dead, we want to look at everything. That's why we look at our starting system, why we look at our charging system. We look at the whole vehicle to try to figure out what is causing the customer's complaint. And if we don't see anything obvious, we need to go back and interview the customer again. Sometimes we find out, oh, well, this is my vacation house here, and my car sits for 6 months at a time, and it never starts when I come back 6 months later. Okay, you're not using the car as designed, so it's not surprising I didn't find anything wrong. Now we need to look at putting a battery tender on the car that keeps it charged up while you're gone, other things, because the customer's using the vehicle in a way it's not designed to be used. And that happens all the time. Where customers use a vehicle in a way it's not designed to be used, but yet their complaint is the symptom with not the whole backstory. And that's why it's important when we do testing, if we don't find anything wrong, go back and interview the customer. Odds are the answer is somewhere in the interview. And many times as a technician, we don't get that information. Either the service advisor doesn't ask it or they didn't think it was important for us to know. And that's why when everything tests good, quickly, fairly quick test, if everything tests good, we need to go start asking questions. And remember what I said at the beginning of this class. This class is all about asking questions. We need to figure out what the customer's complaint is or concern is and how that fits with the facts that we're able to find, and then develop a scenario where what we're finding makes sense with what the customer's concern is. So what we're doing here is we're going to use a separate machine. And I can do this a couple different ways for testing starter draw. I can use a dedicated machine like we're using here, or I can use an amp meter clamp onto a DVOM, DMM, or a lab scope and also get this information. So I don't need a dedicated machine to do this test. So even though in the demo I did show some dedicated equipment, I can get there with just an inductive amp clamp and a voltmeter, and I can do this test. So I don't need a $2,500 piece of equipment or even a $300 piece of equipment to do this test. So, I mean, they have different levels of equipment, just like anything, they have different levels of car. A Honda is not a Lamborghini. They're different cars. They both have things in common. They're both going to get you to your destination. So they'll both get you there, and tooling's a lot the same way. So prepare the starter tester by setting it up and measure to connect starter current. Connect the red lead to the positive terminal of the battery and the black lead to the negative terminal of the battery. So I want to know what the voltage is while we're cranking. So if I was using just a DMM, I wouldn't be able to do this because I would be only able to measure current. I wouldn't be able to measure current and voltage at the same time. If I'm using a graphing multimeter or a lab scope where I could look at two channels of information or two sets of information, then I could look at my voltage while cranking and I could look at my current at the same time. So the dedicated equipment lets us do both. And here you connect the amp clamp either around the positive or negative battery lead. So here in the picture, they're connecting the clamp around the positive terminal right next to the starter. Probably the hardest place to get to it. Why wouldn't I go to the positive cable at the battery or the negative cable at the battery where it's easy, right? Because we know the starter's the load, the battery's the power supply. That's a circuit. Start the battery, go through my switches, conductors, solenoids, through the windings of the starter back to ground. So I can measure current anywhere in that loop. I don't need to do what they did in the book and go down to the starter. That might be very, very hard to get to because the current at this end of the cable is going to be the same as the current at the battery end of the cable or the solenoid end of the cable. So I am not confined to having to hook it up to a spot like this that's extremely hard to access. Again, understanding electricity, understanding Ohm's law, and understanding the rules we have for series circuits or parallel circuits allows me to test where it's convenient, not necessarily where the instructions are or where the book is teaching you to test. Because again, keep in mind the information we're trying to get. I'm trying to understand the amperage or current flow going through the starter, which means that I can go anywhere in the starter circuit and get that information. Let's see. Stop beeping. Ooh, that was a lot yesterday. make sure all appropriate wires are inside the clamp completely closed. So in order for my inductive clamp to work, it opens up and then I have to close it all the way. If I don't close it all the way, it will not work. And like I said, this is an inductive clamp that's part of the machine. I also have inductive clamps that just go right onto a meter. Disable the engine from starting by one of the following ways. I could use a clear flood method. This mode is programmed by manufacturers on many electronic fuel injection vehicles. It can be activated by holding the throttle down to the floor before turning the key. If the engine starts, lift your foot off the throttle right away because the engine is going to speed up very, very fast, and try another method. So some manufacturers actually they stop injector pulse when your foot's to the floor while cranking. I could pull a fuel pump fuse or relay, run the engine until it dies so there's no fuel there. I could disconnect all the fuel injectors or all the coils. I could disconnect the spark plug wires. There's a lot of ways to get there, and I actually got there a different way on my video. I just didn't turn the key on. Right? So there's a lot of different ways. I'm sorry, was that a different video I used? No, that was a different video I did that on. I'm sorry. So yeah, I just unplugged the electrical connector going to all my coils. So I need to, on this one, so I need to disable it so I can crank it long enough to really see what's happening. Many times, if I'm able to record the information, just holding your foot to the floor is enough. Other tools don't require you to do anything, like the Midtronics, and it's so quick. It just wants you to start the vehicle normally, and it's going to look at it in 0.8 of a second and give you all the numbers. So as tools have advanced, we don't necessarily need to do it to test the starter. But keep in mind, the Midtronics is not testing amperage. It's looking at voltage drop and how long it took to do. So it's inferring amperage by the voltage drop based on size of the battery and what I'm working on. But if I'm going to use old and I actually want to see what's going on, I do need to disable my ignition or disable my fuel. I recommend disabling ignition normally. It's easier. The problem with disabling fuel is you still have ignition. So if there's any hydrocarbon vapors present, the engine is going to want to try to start, so it'll crank unevenly, which is going to change the readings and give you bad information. So I really recommend only disconnecting ignition and not disconnecting fuel for the cranking test. With the engine disabled, crank the engine and read the amps and volts as soon as the amps stabilize. Compare the readings to specifications. So my voltage can never go below 9.6, and my amperage is going to be based on the size. So right here, I'm right about 100 amps. So that'd be a little high for a 4-cylinder. It'd be great for a 6 or an 8-cylinder. This is a VAT 40, so this is an old machine. We do still have one at the college. This was the premier machine for doing this in the 70s and 80s. And this was really the standard of the energy. Matter of fact, it was actually just called a VAT 40. It was made by Sun, but everyone, even if it wasn't made by Sun, it was called a VAT 40. So it kind of achieved Kleenex or Band-Aid standard as far as naming. But again, if my inductive clamp is facing the other way, my amps would go positive instead of negative. Again, I'm looking for the total number of amps on this test. I don't care about direction. For the charging system, I care about direction. For this, I don't, because I know the amps are coming out of the battery and into the starter. I'm just looking for a number. So don't get obsessed on which way it's going. So here I'm reading that the starter is using 100 amps. I could look at the other way and go, well, the battery is putting out 100 amps. I mean, so it's we're really about what's the number and what's the voltage. So one of the other tests I did was a voltage drop on the starter circuit. So here I'm going to connect my digital multimeter, black lead to, in this case, battery positive post, and the red lead to the input from the starter, not the input of the solenoid, unless the only terminal you can access. And we're going to crank the engine and read the difference in voltage between what's going in the starter motor and what I have in the battery. So even though I'm on positive and positive, I'm going to read the amount of voltage drop in the circuit. In this case, 136 millivolts, which is acceptable. I would also want to check the voltage drop on the ground. So I would do the same thing. I'd go to the negative battery post and the starter housing and crank the engine over. And if the voltage drop is more than 200 millivolts or 0.2 volts, I have a problem. I also want to test for the trigger wire. So this is the S wire right here. There's the battery cable. And the S wire is what comes either from my ignition switch or comes from my starter relay or computer. And I really want to be within 10% of battery voltage here. So what we're doing here is we're going to connect the DMM to measure the voltage drop on the positive side of the control circuit, connect the red lead to the control circuit, and connect the black lead to the positive battery terminal. And I'm going to crank the engine over and look for a number. And you can hook up the way you're really just looking for the number. And so, you know, what I would be looking for is I would actually leave the red lead on battery positive and put the black lead here, which would give me a positive amp rating because I'm a positive voltage drop rating, but it doesn't, we're looking at the number, not so much the direction. But I want to be within 10% of battery voltage at my trigger, at my S wire. Because we are going to use battery voltage between relays. A relay can use 300 millivolts. It's a switch. I got other wires that are going to use electricity. So to lose 700 millivolts is not uncommon. If I'm losing more than 10% of my battery voltage, so 1.2 volts, if I'm losing more than that, that is a huge red flag, and that is enough to cause the solenoid not to function properly. And that's why we use that 10%, even though that's well above what we should drop. Some systems go through some transistors. And these transistors will use 0.7 of a volt, 700 millivolts. So there's some other systems. So a good rule of thumb is that 10%, because if it's less than 10%, that's not my problem. If it's more than 10%, it very well could be my problem. So that's why we use that 10% rule on the S terminal. So if I look here with the meter, measure voltage drop on the ground side of the circuit, like you did in step 3 of the previous drill. If the voltage drop is more than 0.2 of a volt on either side, use the wiring diagram to measure the individual voltage. And the issue I have with this is we're not showing it. We're not showing the ground coming off here. So we know this wire has to go to ground, and I'm measuring the ground side of the relay for voltage drop. Again, if the relay works, it's not my problem. So this is something we would only do if I don't have voltage here or I don't have what I'm expecting to see. And that's where those relay testers are really advantageous, because with the relay tester here, I'm able to access all 4 of these points. So obviously, if I turn the ignition switch to start and I have my voltmeter going between here and here, and I'm dropping 12 volts and the relay doesn't work, it's a bad relay. If I'm not dropping 12 volts, I have a voltage supply problem. So the book tends to go into breaking down, each side of it is a place that you'd start. In reality, that's not what we do. We start big and then go in the direction of where there's actually a problem. So when testing the trigger signal at the starter solenoid, what is the minimum percentage of battery voltage that should be present?
90.
Yep, 90, number 4. Because I said we're allowed to have a 10% drop. It has to be within 90%. So, absolutely. So let's look at what we're actually doing with some of the voltage drop tests. So I have some old school pictures here to really kind of show the tests I was doing in the lab and show what we were talking about in the skill drill and CDX, which I think is a little more confusing than this. This is pretty simple pictures. We can see how we're going. Keep in mind, of course, the starter is grounded back through to the battery. So I'm going to do a couple of different tests. The first test I'm going to do is on my negative battery cable. I'm going to kick my voltmeter positive lead to ground, negative lead at the battery post. And I'm allowed a maximum of 200 millivolts or 0.2 volts while the engine's cranking. So we test this while the engine's cranking, because if I'm going to find the restriction in the battery cable, I got to have what? Rush hour traffic. I got to really be having a lot of current flow go through that battery cable. So I have to test that while I'm cranking. So this is my battery ground cable test. I also want to test my positive battery cable. Here, I'm going to put the positive lead at positive battery, negative lead here. What we want to do when we hook up a meter, contrary to what the book's doing, is you always want to hook your positive lead to the most positive part of the circuit and your negative lead to the most negative part of the circuit. And that is why here we put the negative lead on ground, because the ground of the battery is the most negative part of the circuit. So my positive lead went here. However, when I go to the positive battery cable, now this is the most positive part of the circuit. So I'm going to use my positive lead here, and my negative lead is going to go here. And again, I'm allowed 200 millivolts on this cable. Up to 200. A good cable will have almost nothing. The next test I'm going to do is across my solenoid. So my solenoid is a switch. So switches are allowed a 300 millivolt drop or 0.3 volts. And that's going from the battery positive side of the solenoid to the output of the solenoid that would go to the starter. And the most I'm allowed is 300 millivolts. So my total drop between the battery cable, which is 200, and my solenoid is 300, is I'm allowed to drop half a volt between here and here, total. So I can have a battery cable that maybe has 220 millivolt drop. It's out of spec. Okay, so it's bad. It's out of spec. However, my drop across my solenoid is only 100 millivolts. So my total between the two is only 320. I'm allowed 500. What that means is two things. First of all, the battery cable is bad, but it also means that the battery cable is not the problem as to why the car is here. And that's really important, because there's a lot of things that test out a specification on cars. And when people are inexperienced, they replace everything that's out of specification without thought to whether it could actually be the problem that I'm trying to fix. So what happens is people buy a lot of parts, they put a lot of parts in, they still have the original problem, but they've replaced all these bad parts that are out of specification. That's because we're not always taught to think, wait a minute, is it good or bad? It's bad. Could this cause the condition I'm trying to fix? If the answer is no, I need to make a note of the bad part and then move on and continue with my testing until I find what could be wrong in causing the complaint or the concern that the customer has. In this case, I know my starter will work correctly with up to a half volt drop between battery positive and the output of the solenoid. So if I'm only dropping 330 millivolts, that's well under half a volt, and my starter's not working, the bad battery cable is not why my starter's not working. That being said, when I replace the starter, I'm going to recommend replacing the battery cable because we know it's bad. Or when I do whatever I need to do to fix the car, it's still going to be, I'm still going to advise the customer that it's out of specification and give them the choice. Because if it's out of specification today, is it going to get better? Or is it like a piece of fruit that started to rot and it's just going to get exponentially worse? So I want the customer to own that decision, not me. They're paying for information. So I'm going to let them know everything I find that's wrong, but I'm also going to let them know here is what it needs to fix the vehicle. The other things are what we should do to keep the vehicle reliable. So what is the maximum amount of voltage drop allowed on a battery cable during cranking?
And number 2.
Number 2, 200 millivolts or 0.2 volts. And you can see
Yes.
here, I'm using both terms, both the 200 millivolt and 0.2. As we move on, I'm going to give you one or the other. So it is important that we know 200 millivolts is the same as 0.2 volts. So as we move on, you'll see different exercises where I don't give you both choices. You're expected to be able to convert these back and forth pretty easily. So I also want to check for the good engine ground to the starter. So just like we would have done with the battery cable, I can bypass the cable test and I can go straight to ground. So again, while the starter is cranking, I measure from the starter housing to battery negative. I'm allowed a maximum of 200 millivolts or 0.2 volts. And you say, wait a minute, that's the same amount as the cable. You're right, but it's the same amount here. This is all either solid aluminum or solid cast iron. I should not have any resistance there. If I do, I have a connection issue somewhere. So I'm allowed 200 total. So even though I'm allowed 200 on a cable, I'm only allowed 200 from here all the way to here. So you can see where if my cable is right at 200 and then I have some corrosion other places, now I can end up out. So we normally test, depending on accessibility, right to the starter case. But if the starter is hard to get to and the other end of the battery cable is easy to get to, we'll start there. Inspecting relays and solenoids. Test a relay, measure the resistance of the winding compared to specifications. If out of specifications, replace the relay. Don't ever do that. If it's in specifications, it doesn't mean it's good. If it's out of specifications, it may still work. And we always want to test these in a live circuit. So this is what the book has. That's why I left it in there. No one does this because it's not accurate and you're not getting good information. So a couple of different ways. We can either use the relay tester I'm going to show you on the next page, or we can apply some common sense. So this is my starter relay, and this is my horn relay. They're going to be the same relay, just like these 3 relays are the same relay. So odds are your car comes with some spare relays that work. So if I had a car that wasn't starting and I thought I might have a relay problem, could I go push the horn button? And if the horn works, would that mean the horn relay works? And at that point, could I take the working horn relay and put it in for the fuel pump relay and then see if the car starts? And if it starts, that would tell me that, oh, the relay was bad. If it doesn't start, obviously the relay is not my problem because I just put a relay in that I know is good. Are you following the logic there? And the next question is, could I do that much faster than looking up specifications? Looks like you're having trouble with your microphone, Vlad.
Yes, I think.
Okay, good. So you can see, even though I talk about some fairly technical stuff or fairly advanced stuff, a lot of stuff we do is literally that simple. Again, is how do I get the most information for the least amount of work? How do I use the tools I have available to me? Well, if I have and this is true whether I'm diagnosing a fuel pump system or anything else, I have other relays that I can verify that they work very quickly that I might be able to swap out for the relay I think might not be working. And we do this all the time. So this is something you should never be doing. There's just no reason for it. This, on the other hand, is a great tool. So here you've taken the relay out, installed this under the relay, and plugged the relay back in. Now I can connect a meter or a power probe or a lab scope, whatever I want to do, and watch the relay work in a complete circuit. I can measure the voltage drop across the winding. make sure it's getting all the voltage it should. In this case, we had 11.7. The relay should work at 11.7. I can also measure the voltage drop across the switch contacts, see if I have high resistance there. I can see if I'm getting told to turn on, so I can see the whole circuit from this point with this in a wiring schematic. So that's why these tools are real popular, is because it just creates that accessibility. You see, I can't get to the underside and I want to test a complete circuit. So, you know, it makes sense to use a tool to see those things happening. And here you can see this is the big relay, square one. These are rectangular ones. See, there's 1, 2, 3, 4 of the same relay. So if I think one of them is bad, do I have 3 spares that I could try to see if it works?
Yes.
Right. And that's a lot of information with a little bit of work, isn't it?
Sure is.
So a lot of what we do is simply just common sense. I mean, we have some really cool tools. We have some really advanced techniques, but I'm only going to go there when I have to. It's just like when I go down to my tree and I want an avocado. I'm not going to haul my 12-foot ladder down there and my pole every time I want an avocado. What am I going to do? I'm going to pick the ones that are low first. Then when I know, there's no more low ones, I'm going to take the pole down and I'll work on getting some of the pole. And then finally it's, you know what? I need to take the ladder down because all that's left is the ones that are really up there. Right? I don't think anyone's going to take the ladder down first, climb to the top, and go past all the easy fruit to get to the hard fruit. So this talks about voltage relay, not the contacts. At the contacts with it not activated should be near battery voltage. In other words, we should be dropping all of our voltage across the switch if it's open, because we have voltage potential on both sides. And then it should be the same when it closes. We should have 0 drop. And I need to change that. It says more than 0.2 volts in the book. It should be 0.3. So that's a wrong number. I need to fix that. What else? It's not going to stop right now. I'll go back and do it. Here, test the starter solenoid voltage drop across the terminals with the key in the crank position. So again, just like the test I explained on the diagram, here's a picture of us actually doing it at the starter. So here's the positive post. Here's the output. The book has the leads reversed, but other than that, you get the idea. The next thing the book talks about is if the solenoid does not click with the key in the crank position, remove the electrical connection from the control of the solenoid, and then use a jumper wire to apply battery voltage to the circuit on the solenoid to see if the solenoid clicks or if it starts. So I'm going to back up here and ask you, so we're taking the time to take this wire off, and then we're going to apply power here to see if we can make the solenoid work. My question is, why are we taking this off? And do we need to? Well, first of all, we don't need to. And the book's giving us bad advice here. This is why we're taking it off. Because what the book's looking at and going, if we put power here, where it's going to put power on this wire and it might hurt something up that wire. Well, that wire is going to what? An open switch. Can I flow any current through an open switch?
No.
No. So therefore, can I hurt anything with having that wire connected and applying power? No.
No.
All I'm going to do is put power on this wire that goes nowhere. So why would I take the time and effort to disconnect a wire I don't need to disconnect just to put power here and see if the starter clicks or turns over? No reason to. Again, once we understand how a circuit works and understand that the other end of that wire is an open switch that can't have any current flow through it because it's open, I know I can't hurt anything putting power there. Therefore, why did they put that in the book? Because the book wants to be over careful that no one ever could hurt anything. So instead of explaining how things work and why I don't have to disconnect it, they're just telling you to disconnect it. And to me, it's all about the why. If I need to do something, I don't care if it's a flow chart or procedure, I'm going to ask, why are they having me do this? Whether it's what are they trying to have me prove? What are they trying to have me protect? Why are they having me do this? And when I look at that and get the why, many times the why doesn't make sense and I don't need to do that. On the other hand, many times the why does make sense. At least now I understand better what I'm testing. So it's really all about understanding. And so it's really important to ask those questions. Not blindly go on, but when you see something like that, wait a minute, why are they having me disconnected? Oh, because they didn't want to train their technicians. They're worried about keeping this stuff up, or I could actually mess something up. So here's a Ford starter solenoid. And the Ford starter solenoid, we can connect a voltmeter, do a couple different tests. One is across the windings. So I have an S terminal here. We're going to apply power. There's a plunger in here. As the plunger moves, it connects this to this and allows voltage to go down to the starter. Here I'm doing a voltage drop test on what? The connection. So here's the battery cable. Here's the post. And I've actually had vehicles not start because there's enough voltage drop between here and here, even though this is tight. So it's tight physically, just not tight electrically. So again, it's a solenoid, 0.3 of a volt or 300 millivolts across the contact. It's a switch. Big switch, not a little switch, still only allowed 300 millivolts because the size of the switch is proportional to the current flow that's going to be going through the switch. Therefore, we use the same specification of that 300 millivolts. What is the maximum amount of voltage drop allowed on the ground side of the starter circuit while the starter is operating?
Number 3.
Not number 3.
Oh, hold on.
4.
Operated. Voltage drop allowed.
Not number.
Oh, it's number 2.
It's number 2. Because I said we're allowed 200 millivolts in a battery cable, and I said on the ground circuit, we don't get any extra for going through the engine block. So it's 200 millivolts total for the ground circuit between the starter and the battery cable. What is the maximum amount of voltage drop allowed on the starter solenoid while the starter is operating? Well, what's the solenoid?
Number 4.
It's not number 4.
Number 3.
Number 3, because the solenoid is a switch. Switches are allowed 300 millivolts. So one of the issues we have with cars that don't crank over is differentiating between electrical and mechanical problems. So we think of our starter as electrical device. It's not working. It must be an electrical problem. But in reality, there's other things that can cause the starter not to work. So typical electrical problems can cause the starting system problems include loose, dirty, corroded terminals, connections, discharge or faulty battery, faulty starter motor, or faulty control circuit. Mechanical problems may cause the starting system problems include seized pistons or bearings, hydrostatic lock for liquid in the cylinders, like from a blown head gasket, or overfueling, incorrect ignition or valve timing, seized alternator, seized AC compressor, and so on. So it's always check for the most common and easiest faults first. Measure the starter draw. A slow crank accompanied by harsh starter draw may indicate low electrical resistance, a short circuit in the starter circuit, or a high mechanical resistance in the engine, such as a seized piston or engine that's trying to seize, causing too much drag. A slow crank accompanied by low starter draw indicates high electrical resistance in the starter circuit or mechanical resistance resulting from a slip timing belt, reducing engine compression. And really, I need to fix that. That's right out of the book. But you won't get a slow crank from a hop timing belt. You get a fast crank because you have less compression. I'll fix that. That should be a fast crank, not a slow crank. Getting right out of the book. If electrical resistance fault is suspected, check for excessive voltage drops. Place voltmeter lead systematically in the starter circuit to locate the place of voltage drop. Use the wiring schematic. You never want to use an ohm meter to check the resistance in the components. We're going to do it all with voltage drop. Voltage drop's more accurate. Why would I use an ohm meter? Now we're doing the same test again. Voltage drops already told me if I have resistance. Why would I get an ohm meter out and test everything again? That's silly. But again, right out of the book. And a lot of times I leave this stuff in here that's in the book. Just so that I can correct the book, because I know you're working on the CDX, and doing that, I want to make sure you understand the difference between what the book has and what actually makes sense for what we do in the real world. If a mechanical fault is suspected, check oil and coolant for signs of contamination, disable components and visually inspect, check compression on a few cylinders. Slow and no crank can be caused by both electrical and mechanical faults. So one of the issues that we have is that if I have, because we have a serpentine belt on the front of the engine now, which we'll see in the next spot on charging system, and that's that wide belt that connects everything to the engine, your AC compressor, your alternator, power steering if you have it, and so on. Well, if something keeps that belt from turning, it can actually be enough to keep the engine from turning. And so it'll act like a bad starter. You turn the key, you get click, 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 or really a loud click, and it doesn't want to go anywhere. And you think you're fighting an electrical problem or a bad starter, and it's actually going to diagnose as a bad starter. But before you replace the starter, because you follow the procedures, it's going to tell you, hey, replace the starter. It's pulling too many amps and it's not rotating. It's bad. What you always want to do is check and make sure the engine physically can be turned over. And you do that by taking a socket and a ratchet on the crank pulley and rotating the engine. And we want to make sure that we're able to rotate the engine. If we can't rotate the engine, that's a whole different thing. That's not the starter's fault normally. Unless the starter went bad and actually wedged itself into the flywheel, which I've seen a couple of times on Fords. Very, very unusual. I've seen it twice in 40 years. But what I have seen a lot is something like the AC compressor pulley on it doesn't turn anymore. And there's enough surface area on that to hold the belt in place. So if the engine doesn't turn over, the first thing we do is take the belt off and then try to turn the engine over. If the engine still doesn't turn over, at that point, we want to take the starter out, verify the starter's not bound up. And at that point, if the engine still doesn't turn over, it's time for an engine. So that is the process. Like I said, the starter is very, very rare. I have seen quite a few AC compressors. We even had one at the campus since I've been there. And they were all set to put a starter in it. And fortunately, I put the brakes on them and said, does the engine turn over? No, because the starter's bad. No, can you turn it over by hand? We didn't check. Let's go check. And we went and checked, and sure enough, you couldn't turn it over by hand. We took the belt off, and then the engine turned freely. We checked, and it was the AC compressor was bad. So I had a team of students, and it was a student's vehicle. They would have put an expensive new starter in their car, because even rebuilt those starters for the vehicle they were working on are close to 200, 150, 200 bucks, and would have had the exact same problem when they're done. And it's not just students that do this. There was a Ford dealership in town a number of years ago that sold a customer an engine on their truck. And the customer bought the engine. So they put the whole engine in, put it all back together. When they put it all back together and went to start it, it went click, click, wouldn't start. Went out to check, couldn't turn over the new engine that they'd just been turning. When they assembled it, found out the AC compressor was seized. So here, a dealer technician at a dealership sold a customer a complete engine, probably to the tune of about $7,000-8,000, because they misdiagnosed it, and what it needed was an AC compressor. So this does happen. The tech got fired, but it does happen. So that's it for starting systems. Any questions before I move on to charging? Okay. So our alternator, commonly called a generator today, supplies electrical energy required for modern vehicles whenever the engine's running. Now, hybrid vehicles use a motor generator that generates three-phase high voltage electricity and then is converted into low voltage DC through a converter. But for conventional vehicles, we're using an alternator. Now, when OBD2 came out, the term OBD2 uses for an alternator is generator. So GM, for example, calls it a generator today, where other manufacturers call it an alternator. Now, this gets real confusing because in the past, we had generators. Matter of fact, all cars had a generator. And we did this into the 1960s. And a generator looked very similar to a starter as far as the housing and the armature and the brushes. Didn't have but it was a DC generator, direct current generator. DC generators didn't charge at idle, and they were very heavy and very limited on the amount of current that they were able to put out, and also didn't last exceedingly long. So in the 1960s, alternators came out, which gave us several advantages. They're smaller in size, put out more power, and last longer. Sounds like a great deal. So we all went to alternators in the 1960s. But to confuse things, in 1996, actually 1994, when they were doing all the OBD2 terms, they decided to call it a generator instead of an alternator, even though we have generators that look nothing like our current alternator. So you can see where we kind of get some naming. So if someone's talking about a generator and they mention the word generator, you kind of need to ask, what your car are you working on? Oh, I'm working on my 55 Chevy. Okay, that's a DC generator. I'm working on my 2015 Chevy. Oh, that's an alternator. So you see where this can be a little bit confusing, and you're going to see these terms used back and forth and not necessarily cleanly. So I kind of wanted to give you the history and for you to understand what a real generator is and what an alternator that's called a generator is. So inside, DC generators use rotating wires in a stationary magnetic field. Alternators use a rotating magnetic field and stationary windings. So if I look here at my old school DC generator, doesn't that look a lot like a starter that we just looked at yesterday?
Yeah.
All my commentator segments, brushes, everything, rotating permanent magnets. That's why I said, so that's why I mentioned, remember I mentioned yesterday that if my overrunning clutch or my Bendix sticks in the flywheel and the engine starts, my starter actually becomes a generator because it's basically the same thing. It's just a matter of, are we applying power to make it spin or are we spinning it to make power? That's simple. Now over here, my alternator, now I'm rotating the magnetic field, and I have 3 field coils. Alternators make AC electricity. Generators made DC electricity. Not only am I going to make AC electricity, I'm going to make 3-phase AC electricity. So superior operating characteristics of alternators include greater wattage output at low RPM, higher RPM capability of the unit, smaller physical size and weight, and greater reliability, longer service life. DC generators and alternators produce electricity by relative movement between the conductors in the magnetic field. The main parts of the charging system include my battery, my alternator, my voltage regulator, charge warning light, and wiring. So on a vehicle, the most positive part of the system when the engine is not running is the battery. As soon as the vehicle starts, the most positive and most negative part of my electrical system is the alternator. So the alternator is more positive and more negative than the battery because that's where the electricity is now being generated from. So charging systems have to be controlled. So both generators and alternators both used originally an external voltage regulator. Now voltage regulators are either built into the alternator or we're using computers to control the voltage output. So the next generation of charging systems included regulators that were incorporating the alternator. More recently, PCM was used. So here's an old mechanical voltage regulator. This would be mounted on a fender or a firewall, separate from the alternator. And you would have wires connecting into the alternator. So if this charging system wasn't working correctly, I had to test the alternator separate from the voltage regulator. That being said, on these systems, I could replace a bad voltage regulator if the alternator was good. If the alternator is bad or generator is bad, I need to replace the voltage regulator at the same time I replace the alternator. So in other words, the voltage regulators could go bad, alternator's fine, put a voltage regulator on it. But if the alternator was bad, even if the voltage regulator was working, we always want to replace at the same time. These did not have an extremely long service life compared to what we think of things lasting today. So if I look at my voltage regulation, I've got my stator and I've got 3 windings, and each of these is going to make electricity, and it's going to go into here, and it is going to be rectified with positive and negative diodes. And then I'm going to have diodes here, and I'm going to get DC electricity out, and it can come down over here to my field coil, which excites it, my regulator, and a protection diode and a lamp. So on these systems, if my warning lamp goes bad and the bulb's bad, the system won't work. So I've seen people put 3, 4 alternators on a car because the bulb is out in the dash. System will not work without the bulb. Or in the case of like early 2000 GM trucks, the gauge fuse is blown. I've had a guy put 2 alternators in a vehicle because the gauge fuse was blown. You think it would have been included that none of the gauges work, that maybe we want to look at something, but we were so focused in the battery's going dead, it's a charging system problem, we didn't step back and look at the whole picture. So if I'm doing charging system diagnosis, one of the things I always do is look to see, does the charging system gauge work or does the charge light work? If it doesn't, that's a red flag. Okay. Now it might not be working because the alternator is bad, but I am going to need to do some electrical testing at the alternator to verify the integrity of this signal, and then I'm getting power to the alternator on that wire. So I'll need to do some testing. Can't just assume everything is in the alternator. So what we have here is we have a voltage regulator, and the voltage regulator controls the current through the field coil. So once the car starts charging, now power comes through here. The issue is it won't ever start charging unless the power through the warning light comes through the field coil to the regulator. The intensity or the amount of current through the field coil determines how many amps we charge. So what we're doing is we have the capability of charging 6 amps or charging 60 amps, depending on the amount of current flowing through the field. So if you've heard the term full fielding an alternator, that means we're flowing power and ground with no resistance through that field coil to get the alternator to output the maximum amount of current that the alternator can put out. And in the old days with external regulators, that's what we did. We would bypass the regulator, full field the alternator, and see if the alternator puts out. If it does, it needs a regulator. If it doesn't, it needs an alternator and a regulator. So we would full field the alternator in order to see if the alternator works at its rated capacity. And alternators have an output rating. Old cars, 35 amps. Then we went about 55 to 65 amps. So it was very, very common for a lot of years, 80s, 90s. When we get into the 2000s, a lot more electronics, 85 amps became kind of the standard. And we do have systems up to about 165 amps for a regular alternator. BMW has some alternators that are over 200 amps, but they're liquid cooled. So they're still driven by a belt, but they're cooled by liquid, not by air. So we've come a long way from that 25 or 35 amp alternator that we used in the 60s. Again, but we have a lot more electronics on a car now than we did in 1967 with manual windows and a 6-cylinder engine and no AC. So here is another picture of basically the same type of system, just different picture of it. So we can see here an ignition switch with the charge light. I come down, here's my field coil, here's my regulator, here's my stator windings, and here we have our diodes. So I have positive, negative diodes, and I have a diode trio that allows DC voltage to come back. And what causes the charge light to go out is that the charging system is putting voltage here. If the charging system doesn't put any voltage here, then I have power here, but this side would connect to ground through my regulator and the charge light comes on. So in actuality, it's the regulator that turns the charge light on. So if my regulator goes bad, it could cause my charge light not to work. In other words, if it melts internally and no longer connects that circuit to ground. Ford Tauruses did that a lot. So that can happen. So keep in mind, that's why we would, if my light doesn't light up, I need to verify I'm getting power from the ignition switch through the light bulb to the alternator, which tells me what? The light bulb's not burned out. If I don't have any power there, my alternator might not be working because of what's happening inside the dash. And we want to know that before we put an expensive alternator on a vehicle. So here's a couple voltage regulator and an alternator assembly. So here is an alternator assembly, and it has an internal voltage regulator right here. So there's 3 wires going to this particular alternator. One is a power wire that goes to the battery. This is a power wire from a fuse box. And this little white wire is the one that goes to the gauge or warning light. So if I unplug this and I don't have any power on both of these wires, my alternator will not work on this system. And the mistake, because this system is a very easy system, people really like this GM system because it works easy and reliable. But people would get lazy and not unplug this and verify that I have power at both of these with the key on, engine off, and would just throw an alternator in it. What else could it be? It has to be the alternator. And they would do that 2 or 3 times in a row before they finally go get a book and find out, oh, wow, there has to be power going into it for it to work. This is another voltage regulator. This is Bosch. And this one actually comes with brushes in it. So this was kind of a neat idea Bosch had, is that when you change they figured if they're, and this mounted on the back of the alternator. So they figured, you know, if it's been on here long enough to not work, let's give you a set of brushes also. And you would drop that in and it gets new brushes and a new regulator. Kind of a really neat idea. And we did a lot of these because that then the alternator's down to either one thing that's going to make it not work is either a bad spot in the windings or the bearings are bad. So instead of having to replace the whole alternator, many times we just put a new regulator and brushes in. Very, very common repair on those vehicles. Here's an example of a mechanical regulator. So here's a brand new one I had on the shelf. And so we haven't used these in a long time. It's mechanical, not solid state. So you're talking, 70s, early 80s. This is right here is probably Asian. So I'm guessing Toyota, Nissan on this. Probably Nissan by the connector. But this has real fine wire and a winding that when current flows, it generates electromagnetic field. And based on the field strength, it is going to make a connection or not make a connection on the electrical connector. And so basically these are just tapping on and off to constantly in order to regulate the amount of voltage the alternator is producing. So you can see why these last forever by any means. So limited amount of time. Newer vehicles, we have computer controlled charging systems. So here's a battery cable, actually has a sensor built into it. Here's another battery cable, it has an amp sensor built into it. So if you see this on a battery cable, that's your first clue that you definitely have a computer controlled charging system. Now, there are computer controlled charging systems that don't have these things on it. So just because this is missing doesn't mean it can't be computer controlled. All this means is that I know it is computer controlled. So don't take the absence of it to mean it's not or it can't be. It could be. But this just means it definitely is. Now, we started computer controlled charging systems, Chrysler did in 1987. So this has been around a long time. Yeah, Dante, did you have something?
No.
Oh, okay. Just saw your screen light up, so I wasn't sure. So if the charging system indicator bulb is burned out, open, what effect will this have on the system's performance? Yep, number 4. The bulb will not light. We know that it's burned out. That's the gimme. But the alternator may not charge. I know have none because I know at the very least the light's not going to work. So that's why number 4 is correct. And I put may not charge because there may be some systems out there that charge with a burned out bulb, especially some of the newer computer controlled ones where the bulb is a function of the instrument cluster module. It has nothing to do with the actual charge circuit. It's all information sent between computers. And that's why I put the word may. You'll find I don't use a lot of always and nevers because there's, what is it on the road right now? There's about 1,700 different models of car on the road right now. And the average age of the vehicle, I think, is right around 12 years. So you see there's a tremendous amount of things that are on the road. So to say always and never usually just means someone hasn't seen enough things. So there's very few things that are always and never. So when I say always or I say never, I really mean it because the rest of the time I'm pretty guarded with that. So electromagnetic induction in my alternators. The alternator converts mechanical energy into electrical energy by electromagnetic induction. A bar magnet rotates in an iron yoke. As the magnet turns, voltage is induced in the coil, producing a current flow. The value of the electromagnetic force induced by an AC generator depends on the strength of the magnetic field, the speed at which the magnet rotates, the relative distance between the magnet and the conductors, and the number of turns of windings in the stationary coil. So you can see I could have a single alternator housing that one of them might be 55 amps, one might be 85 amps, and one might be 110 amps, all in the same physical housing. And this is why it's really important that when we're replacing an alternator, we match up the correct size, meaning amperage output, when we're replacing the alternator, because I can have multiple levels of amperage capacity in the same exact alternator housing. All of them will bolt on the vehicle just fine. But the issue is if I'm supposed to have a 105 amp alternator and I put a 65 amp alternator in, that means I have more things that use electricity on this car then that 65 amp will be able to replenish the battery and run. So while I'm going down the road and I'm using all those cool things that my fully loaded car has, and if my charging system doesn't make enough current, we're going to have to start taking amperage out of the battery. So if I drive long enough, eventually my battery's going to go dead and I'm going to die on the side of the road. Or if I didn't drive that long, maybe my car doesn't start the next time I go to start it, because instead of charging my battery while I drove, I actually took energy out of my battery while I drove. So it's really important to make sure that we have the correct amperage. On the other hand, say I have a vehicle and originally it had a 65 amp alternator, but I've added this really cool stereo in it, and I got this big screen with my nav system, and I got these extra lights on the car. I might want to check to see if they make an 85 or 105 amp alternator that's in the same case that I can just bolt on that car. And now I have enough energy to supply all the TV sets the kids are watching, all the other things that I might have turned on in that vehicle. So a lot of times people upgrade a vehicle by putting new cool things on it. I mean, we all customize our cars or to one extent or another, even if it's just the floor mats you really like, or the thing on the seat, or, I mean, you know, I don't think anyone's car looks like it did when it left the showroom. We've done something in it that we're doing something differently, even if it's our phone charger. So we all, I mean, that's something we all do. But as we make some of these changes, we need to be mindful as do these changes affect other things? And sometimes we don't know till we have a problem, and that's okay. But that also means if I'm working on a customer's car and they're complaining about something, I need to be diligent. Again, instead of just looking at the alternator, let's look big picture. Wow, they got some big cables going back to the amps. Wow, look at these TV sets and the headrests. Look at, you know, they've done a lot of extra stuff on this, and it still has this real little factory alternator that's got 150,000 miles on it. And they got the smallest battery that didn't even have the cold winter battery option. And it's got the smallest battery. So maybe all that stuff tests good, but we're asking it to do things it's not designed to do. And so one of the things we do when we're looking at customers' vehicles routinely is we look to see, is there aftermarket devices placed on the vehicle? Has the customer modified the vehicle? Is it possible those modifications could be causing or contributing to what the customer's complaining about? So that's a very real discussion we have every day in the shop. We have to look at now. So here we can see my alternator, and we can see our north-south on our magnet, and it's going to rotate. So in this case, I have current flow going this way, and it rotates, no current flow. Then it rotates this way, I get current flow going the other way, and then I'm back to no current flow. And it does this on each of the phases. So that's another advantage we have, is that it's happening multiple times with each revolution. So if I look at my AC waveform that I just looked at, one cycle, and the definition of a cycle in electricity is when I start somewhere and then the next time I start at the same place and I repeat the pattern. So here, one cycle would be from here, I'm going up, I'm going down, I'm going back. That's one cycle. You've probably heard the term hertz. So a hertz is a frequency of how many times that cycle repeats in 1 second. So when we talk about our electricity in our house, which is AC, in this country, it's at 60 hertz or 60 cycles per second. If I'm in Europe, it's at 50 cycles per second. It's a different number of cycles. Why? Just because. Just like Europe uses different voltage than we use here. There's just differences. But this is one cycle. So if I only had one cycle, I would need to spin my alternator all the way around, and there's my one cycle. So I'm only getting power I can use when it's positive, and up here, I don't want any of this negative stuff. Well, by having 3 phases, now I've got what? One positive cycle. As this one goes negative, this one's already started going positive. And then as this one goes negative, this one started going positive. So now you can see I'm getting a lot more positive hits through my 3 phases. And we're actually going to make even more than that through rectification. But that's what allows us to get more constant, because what AC voltage is, like the 120 volts you have in the wall, is it's not that it's sitting at 120 volts all the time. In actuality, it's going from about 150 positive to 150 negative 60 times a second. But what we're looking at is we're looking at a number that's about 70% of the peak. And that's where our average is. That's where our usable voltage level is. And then we need to convert that from AC to DC. But that's where we get that. They call it an RMS voltage. So we're going to look at the alternator component, and then we're going to look at, see how I have all this wasted energy down here, my negative cycles. What rectification is going to do is it's going to flip these negative cycles positive in double the amount of time I spend positive, which is pretty cool. So let's look at the alternator construction. And I don't know if we'll get to rectification today. If we do, fine. It is fairly early yet, so we have a high likelihood of it. And then CDX has a great animation on rectification in it. And so I'll probably pull that up and show it to the class, which I usually do, because rectification seems to really confuse people. Keep in mind, we're not going in and rebuilding these anymore. We're not replacing the diodes anymore. So now rectification is more a matter of why things happen than having to go in and test it. So it's a little different level. So explain the purpose and function of alternator components. The alternator consists of a stationary winding assembly and a rotating electromagnet. So my stationary assembly is my stator. It has a slip ring and brush assembly. So unlike what we did on the DC generator, where we have the commutator and the brushes and the windings are attached and it goes through, even though I do have some insulation for the shaft, it's going through the windings. Here I have little rings that slip on the shaft that allow me to make an electrical connection. So we have the slip ring, brush assembly, rectifier assembly, 2 end frames, a cooling fan, and drive pulley. So if I'm going to be air cooled, I'm going to have a cooling fan either in front on the outside or the inside of the alternator, but they all have a cooling fan. We make these out of aluminum, and we do that for heat dissipation. So although they sell chromed alternators that are really, really cool, they don't last as long because you can't get rid of the heat. They overheat inside. So they look really neat, just they don't work as good. Just like occasionally I see people that they're in the auto shop and they really like yellow, so they paint everything yellow they can find, or blue, or whatever their favorite color is. When you paint an alternator, you diminish its capability to dissipate heat, the alternator will fail sooner, period. And that's why you don't see alternators painted from the factory, is because that porous aluminum housing is designed to dissipate heat. The voltage regulator monitors the battery voltage and varies current flow through the rotor field. The voltage regulator controls output voltage of the alternator to maintain system voltage, normally between 13.5 and 14.5 volts. So, for example, GM, when you first start the car, can get as high as 15.2 volts. If I'm working on a European vehicle, some of these systems will only charge from 12.8 to 13.2 volts. But keep in mind, that still has more energy than the battery, so we're still going to put stuff into the battery. So if my charging voltage is 12.6 volts or less, the charging system is not working correctly. If I'm between 13.5 and 14.5 volts, that's not my problem. In other words, I can look at that and go, yep, it looks good. That's not why my car is not starting the battery or why it's having issues. If I'm outside of that range, either high or low, I need to go do research and find out if it's normal for that vehicle. So this is a real good rule of thumb measurement. We've used it for 40 years. Is that 13.5 to 14.5 volts that the charging system should be putting out. Again, there are exceptions. There are systems that may be slightly higher or lower than this. And that's why if we're not in that range, before we start replacing parts, especially on modern vehicles, we should go look up and see what's expected for that vehicle. Again, very, very common for European cars to have a lower voltage output. Not all, but very common. So that's why I'm not saying if it's outside that range is bad. I'm saying if it's outside that range, go do more research. But if it's inside this range, this is not my problem with the car. Move on. Charging system is working. So another advantage we have is that when I had the stationary magnet, I had to rotate completely to go around that magnet, didn't I? Well, here you can see with the magnets here, I've got what? North, south, north, south, north, south. So every time I'm going north, south, north, south. So look at how many more times I can do this every rotation. That's why generators, DC generators, didn't charge at idle, but alternators can. So electromagnet that rotates freely in the alternator, supported on each end by bearings, consists of a coil of insulated wire wound around an iron core and pressed onto a steel shaft. Now, these slip rings are not connected to the shaft. They're insulated from the shaft. That doesn't mean they're spinning off the shaft. They're connected to it, but they're insulated from it, if that makes sense. But they're electrically connected to the windings in here. So they're electric. So you have one of these is connected to one end of the windings. This is connected to the other end of the windings. And then the brushes transfer that power out. The ends of the rotor coil winding are connected to the insulated slip rings mounted on the shaft. When the rotor is fully energized, the magnetic field is at its strongest and induces the maximum current flow of the stator. So by changing the amount of voltage that we can induce, we strengthen the magnetic field, which creates more power. So slip rings are normally copper bands molded into an insulated material and pressed into the steel shaft on the rotor. Each end of the rotor windings is connected to one of the copper bands. So this is our electrical circuit. The more current I flow through this, the stronger the magnetic field, the more output I get. So this is our field. You heard me talk about full fielding. That's what we're doing. We're fielding the alternator by applying current through here. Brushes are made of a combination of copper and carbon and are carried in brush holders, spring-loaded to maintain contact with the slip ring. So needs to say, the number one item of wear in an alternator is the brushes. Second is probably the bearings. So those are the things that tend to go bad. Now, what we are seeing on some modern vehicles is we're actually seeing brushless alternators. Well, brushed alternators are lasting hundreds of thousands of miles today because the technology is pretty darn good. Imagine how long a brushless one could last. Can we get 1 million miles out of an alternator then? Maybe. So you can see as technology has evolved, the required replacement of these components has become less and less. So even though there's exponentially more cars on the road, we're not necessarily replacing these parts even as much as we did 20 years ago with fewer cars on the road because the technology's gotten that much better. What is the expected operating voltage range for a charging system with no additional load applied?
Number 3.
Number 3, 13.5 to 14.5 volts. And that's a need to know range. I'm going to expect you to know it. I would expect to see this number on, I know it's going to be on at least one quiz. I wouldn't be surprised to see it on an electrical test. This is a need to know thing. This is something that, you know, every technician should know off the top of their head. So brushless alternators, as I mentioned. Induced current flow into the rotor, call them an inductive motor is another name for it. The greater the current flow in the exciter field, the greater the alternator output. So we're still what? Full fielding the alternator, controlling the field of the alternator. So that hasn't changed. We've just managed to get rid of the brushes. So you can see here, we got the exciter windings and stator windings, and we're going to induce the voltage in. Works really slick. So that's what we're going to induce into here. Now let's look at our stator windings. So our stator is what's actually going to produce the power that we're going to use on the car. So here's a picture of a stator. So we have 3 wires in the stator, and all 3 wires are connected together. And I'll show you the 2 different ways we do that coming up. So even though we see lots of loops here, lots of going on, there's only 3 wires. And I can tell you they're all connected together at a center point on this one. So this stator that we see here from an alternator is identical in design to the stator that I have down below out of a Prius transmission that has a motor generator in it. Because motor generators on hybrid electric vehicles are a 3-phase motor, just like my generator is. All 3-phase motors are generators. So it's all about controlling the field, whether you want it to work as a motor or work as a generator, whether you're applying or whether you're getting. So the design itself, all 3-phase motors are also generators, just like all 3-phase generators are motors by design. It's all about how we control the field and the controls on them that gets them to work one way or the other. So if I look at the stator in that motor, other than being a lot bigger than this, and the wires are bigger, but you'll see the same 3 lugs coming out. Technology is the same. We're applying it differently. That's why people that were good with electricity didn't have a big problem when we went to learning about hybrid vehicles. Oh, that's an alternator without this, but with this, and okay. I mean, so it wasn't a big jump. There's a lot of differences. There's differences in how we control it, differences in the fact that we're able to go down the road and do some other things. But as far as the actual physical pieces, it's real easy for us to identify and get our head around because it's very similar to an alternator. And like I said, the stator is identical in appearance, just bigger. So 2 methods of connection used for the stator are phase windings or a Y and a delta configuration. Almost everyone uses a Y. All hybrid vehicles use a Y. I'm not aware of any alternators that are using a delta, but there probably was some at some time. And again, I'm not rewinding it, so I don't care. But the Y method of connection, one end of each phase, the winding is taken to a central point where the ends are connected together. The other end of each winding is connected to the bridge rectifier circuit between the positive and negative diode. On the delta method, the windings are connected in a shape of a triangle. In this arrangement, only one winding sits between 2 legs of the rectifier. So this is actually, the Y seems to generate better power more evenly because you see we're going through 2 at a time, as opposed to here we're just going through 1 at a time. So what we see in automotive is this Y configuration. So remember what I said, there's only 3 wires in that whole stator. They all connect at a central point, and I can see the 3 ends sticking out, and that's what's now attached to my rectifier bridge. And if I look at 3-phase motors, this is exactly how 3-phase motors can be wired, either as a Y or a delta. So if you have a 3-phase motor somewhere, or even a single-phase motor can be wired this way, and they convert it between single and dual, depending on how they change some of the wiring inside. But again, very, very common. So we see that technology go into a lot of other areas. Alternator housings are typically constructed from aluminum with vents in the frames. We can see our 2 alternator halves. provide a large amount of airflow to assist in dissipating heat. A pulley is driven by a belt is mounted at the drive end of the alternator. So we are going to drive it. Now on the frames, some alternators only go together one way. Other alternators like that Chevy alternator can actually be put together 4 different ways, depending on where I want to mount the alternator and where I want the electrical connection to be. And they call that clocking. If I need to reclock an alternator that can be reclocked, like the GM alternator that they use forever, I would take the pulley off. So there's a nut, you pop the pulley off. There's the 4 screws that hold the case together. In the middle of the case is my stator. My stator is attached with wiring to the back of the alternator. So if I try to rotate the back of the alternator, I'm going to break the connection to the stator. So what I need to do is get the front of the alternator to lift off the stator. Then I can rotate the front of the alternator, put it back on, put the bolts back in, put everything together, and I've just successfully reclocked an alternator. Now we used to have to do that. They used to make alternators one way, you got them to the shop and you clocked them for what you needed. During the course of time I've been in industry, people were not stopped being taught how to clock alternators. So they were breaking them all the time. So now from the parts store, generally you're going to get one clocked the exact way that it's supposed to be clocked. Some manufacturers actually put a tag across and say you void the warranty if you reclock it, things like that. But other manufacturers or parts stores may still say, hey, I can't get the right one till tomorrow. You can reclock that one. So now you have a choice of getting the car back to the customer today. The car's already torn apart. It's in your bay. Do you want to take the 10 minutes to reclock it? Or do you want to go, nope, I'm going to push it out and wait till tomorrow and have a customer yell at me? So this is something that's still done in industry. The problem is many people don't know how to do it. And that's why I talk. And really, it's not hard. The mistake people make is they let the stator rotate on the back of the alternator housing. Well, that's where all the wiring is. We can't do that. We can only rotate the front, and you need to make sure that the shaft with a magnet that's on the brushes stays in place, because if it lifts out, then you can drop a brush and it's a pain to get everything back together. So that's why we usually use the screwdrivers. Sometimes they stick on the bearing on the shaft, which is kind of a problem. But that is what we're doing when we reclock an alternator, and that still has to be done. So that's where we see on the cases. Other designs like this only go one way. There is no reclocking. So here we can see the front bearing right here. So we see the powerful fan. Cooling fins and plate, maximum cooling effect. So we can also, so you can see where the bearing is here, the fan, and you can also see right in here where you got the windings for the field coil and also where the magnets. Another thing we have is an overrunning clutch that we put on the front of some alternators. So you notice it because it is covered on the front and it's really kind of big and bulky sticking out. And this reduces belt noise and vibration, reduces stress placed on the tensioner belt, extends belt and tensioner life, and it improves fuel economy. So that's the overrunning clutch. So how to diagnose them? Listening for a clicking, popping, or buzzing sound when the engine is turned off after running at 2,000 RPM. So if I think I have one of these, bring the engine RPM up to about 1,800, 2,000 RPM and turn the key off. And here, if you hear some really nasty popping or clicking sound from underneath the hood, odds are that little clutch piece has gone bad on the alternator. They can be replaced separately. It takes some special tools. The special tools required are fairly expensive, and the actual clutch assembly is pretty expensive. The difference to the customer many times between putting a clutch on, the overrunning clutch on, or replacing the whole alternator is only about $100. So there's not a big price difference between putting a new overrunning clutch on an alternator that already has 180,000 miles on it, because these do last a very long time. or put in a whole brand new alternator that comes with the newer run clutch and you're good to go. So consequently, shops tend to replace the entire alternator. And you're probably thinking, only $100 difference, that's a lot of money. Well, it's all relative. If you're paying the money for the labor and you're paying the money for the part, and if putting the clutch on it is, let's say, $350, and I could put a brand new alternator on for $400 to $450, yes, it's still that $100 difference, but relatively, it's not that much when you figure that the clutch is really the minimum repair and the alternator could go bad next week, and now you are spending the $450. So consequently, customers normally choose. Another concern is that the alternator is on the shelf. I can have your car back to you this afternoon. If I replace just the clutch, it's 3 days away, and I'll get you the car on Friday. So you can see where these decisions influence repair. So rectification, I thought I'd get here today. Explain rectification operation of the rectifier. So the process of converting AC to DC. A rectifier assembly consists of diodes in a specific configuration. A three-phase bridge rectifier has a minimum of 6 diodes. A diode bridge has 2 diodes in series bridged with a wire. And a three-phase alternator, one side of each stator winding is connected to one of the bridges. And what we're going to do is, as we flow through here, current flow through a single phase in the forward direction. So I've got phase coming through here. We're rotating, the rotor spinning, and I am coming through. And then here, current flow through a single phase in reverse direction. So now what happened is, as this is rotated, now what's happened? The direction of flow has changed. So where we were flowing in here, now I'm flowing out here. So I have positive and negative cycle here. So what I want to do is I want to make things all positive. So I was talking about with a 3-phase not rectified, I have an analog AC signal is going positive, negative, positive, positive, negative, positive, and so on. Now this right here is degrees of rotation of my alternator. So 360 degrees, one rotation. And with one rotation, I've got 3 spikes up here, but I can't use all of it. I got to use it where we're consistent. So the lowest I'm consistent right here is my positive. So this is where I could get some steady voltage. However, by using the rectifier bridge, I'm able to flip these negatives positive. So now where is my average? My average is all the way up here, because I have more cycles in that same 360 degrees. Instead of 3, I now have 6. I'm not having to come down as far to hit that intersection. And I have a steadier, more consistent voltage. So very cool how it works. It's amazing that they figured that out using diodes when diodes were fairly new back in the 60s. And to make an alternator, an AC system, and invert that DC to AC. So one of the issues we have with alternators is the rectifier bridges do go bad. So most charging testers have a thing called alternator ripple or AC ripple on them, and it'll flag and say, hey, you have excessive AC ripple. What that means is you're putting AC voltage on top of the DC that's going to the battery. And that AC voltage could damage computers, it can damage other systems or cause systems not to operate correctly. So either my charging system tester will check for that and tell me if I have an AC ripple problem, or I can use a voltmeter or a lab scope on AC and look to see if I have AC voltage at my battery. And if I do, that's a problem. So a couple hundred millivolts of AC, we probably live with. I got a volt of AC, that's a real problem. So that's the alternator ripple. And that is something I actually had someone who worked for AAA in my last class. And she asked me, she goes, yeah, it comes up and says AC ripple on here. But then I hear from customers that they went to a shop and they said everything's fine. And that's because technicians don't understand what it is. Hey, it's bad AC ripple, but then they check, well, the charging system's putting out voltage. I guess you're good. You're between 13.5 and 14.5 volts. That's not what the AC ripple is telling you. The AC ripple is telling you that you have a problem in the diodes, allowing AC current to get into our DC system that could either damage computers or cause computers not to function correctly. So it's important when we're checking a charging system to understand what it is we're actually testing for. So as the rotor rotates, each time the magnetic field changes from north to south or south to north, the current changes direction. The three phases are split and not rectified. By directing the current so that it is flowing in a positive direction, the diodes effectively flip all the negative current flow activity. The top of the waveform is called the alternator ripple. A ripple that is constant across each winding indicates the stator windings and diodes are each creating current flow and voltage consistently. So the rectifier assembly is the actual diodes themselves are mounted on heat sinks. Each diode drops approximately 0.7 of a volt and thus tends to run hot. The diodes must be properly cooled to avoid premature failure. Hence, going back to talk about chroming and painting alternators. One heat sink has positive diodes, the other one has negative diodes. And these are commonly called diode trios. But we have another diode trio also. Some alternators use diode trio assembly to supply power to the field windings once the alternator is charging. So we can see our diode trio here. So let me stop this share. Let me pull up CDX. So I'm in CDX chapter 54, and I'm going to come down here because it's also in the chapter, but I can come down here to my media gallery. And in the media gallery, I can go to animations and alternator rectifier app. So you got brushless alternator, you got all kinds of stuff here, but I'm going to go to my rectifier operation. And here is my rectifier. So here's my phases. So if I just want to look at one phase, two phase, three phase, or all the phases. And so this animation shows the current flow through the star wound alternator and rectifier. Use the blue buttons below to pause, play, or stop through the rotation of the rotor to allow you to see the direction of current flow at any given point. In real life, the rotor is not. In real life, if the rotor is not turning, there is no current flow. So there's a problem with the animation. But as you can see, I've still got current flow, but we're not moving. That's why they put that there. So you can see where we're switching. So this does kind of a nice job of showing how we're going through and where we're sending our voltage. You can see here, I just have the two diode trios. Remember, we're making positive and negative energy, but I want that nice steady 12 volts. I only want the positive coming back through here. So we're rectifying it. And might as well do regulator operation, which is the next thing we're going to talk about. So here I have an internally regulated alternator, conventional system. An internally regulated alternator is a combination of transistors, resistors, diodes, or thermistor to both sense and control the output. So you can see I've got my ignition switch, my warning light. I turn the ignition on. My light is on, okay? Because right now, which means if it's on, I'm able to get to ground. So we've kind of given you the inside of the regulator. You can see we have a couple transistors and a diode. And the Zener diode is there for not only direction control, but to control voltage spikes. And then I go to ground here. So right now we're coming up and we're able to get to ground. This is able to light up. When I start the vehicle, the charge light goes off, and now we are controlling the field on the alternator. So here I'm running. There's faulty. We're still spinning, but where's my electricity? And what? My charge light's on. Now that I'm running, I have current flow through here. So this is positive because I have positive energy coming out of the stator that after being rectified. And since I have positive here and positive here, there's no electrical difference. The light can't be on. As soon as it stops working correctly, now this is no longer positive because we're not charging. Therefore, we will be able to get to ground and turn the light on. If I go to ECU control, now we have the computer. All the computer's now looking at the voltage and giving the command. The light still comes on with a fault. In this example, the light is still wired directly to the alternator. Many new vehicles today, the computer that is controlling the charging will be the one who turns on the light, and the light's no longer attached to the alternator. So that's one of the changes that we've seen.